We are in Chapter 6, Random Variables. So 6.1a is Discrete Random Variables. A random variable takes the numerical values that describe the outcomes of some chance process. So an example would be what we've already been doing, rolling a dice, flipping a coin. So number of tails when coin is flipped, or the number on a die, or we could do the number of children in your family, the number of people in your family. There are lots of different ways we could take discrete random variables. The distribution of a random variable give its possible values and their probabilities. So we are going to put that on a histogram, or we could put it on a dot plot. So histogram or dot plot is a way to show the distribution. It shows how many of each of the values. What is a discrete random variable? And give some examples. So we either have discrete or continuous. So discrete random variables are like shoe sizes. I could have decimals, but I can't have every number in between all of those. Like I could have 7, 7.5, 8, 8.5, 9. But there's no way to get a shoe size of 9.0526. But continuous random variable, that could have decimals, and it's everything in between certain lengths. So let's say it is 8.75 inches or whatever. So foot length would be continuous because you can have a value between all the other values. Discrete, you wouldn't. It's more of counting. So discrete is more counting. Discrete is a fixed set of values, often things that we count. So most of the time they're whole numbers, but an example of not whole numbers would be shoe size. You can have decimals there. Imagine selecting a U.S. high school student at random. Define the random variable x equals the number of languages spoken by the randomly selected student. The table below gives the probability distribution of x based on the sample of students from the U.S. Census at School database. So we have languages, so 1 through 5, and then probabilities that match. We first need to show that this is a probability distribution. So remember the whole probability model. What two things do we have to look at? All probabilities are between 0 and 1. And then the sum of all the probabilities is 1. That's what we need to look at. So all of these are between 0 and 1. So we're good there. And then if we were to add these up, we get 1. Okay, B says make a histogram of the probability distribution. Describe what you see. So here is an example of a probability distribution. So languages would be on the bottom. Probability would be on the y-axis. And then we put numbers here, and then the probabilities. And so one language is 0.63, 2 is 0.295, 3, 0.065, 4, 0.008, and 5 is 0.002. So it has everything it needs, which is all the labels and everything. Then it says describe what you see. So remember back in chapter 1, we had to do socks. So let's start with shape. The histogram of number of languages spoken is strongly skewed to the right. So it goes like that. The tail is on the right. Center. The center is the median, since it's skewed, is one language. This is our center. We would not use the mean because this is skewed right. And then spread. The number of languages varies from 1 to 5, but nearly all students speak just 1 or 2 languages. And then O for outliers, there are no outliers. Let's look at C. What is the probability that a randomly selected student speaks at least 3 languages? So we'd need to find the probability. So this is how we would write it. Probability that x is greater than or equal to 3. Notice this is an uppercase x, and that's an x for a reason like that. So that means I'm going to find the probability that x is 3 plus probability x is 4 plus probability x is 5. So I find those from our table here. Add those up. I get 0.075. Okay, what about finding the probability that the language spoken is more than 3? So when we say more than 3, we're only counting up 4 and 5. So what I want you to notice is when you add those up, we get a different number than greater than or equal to 3. Greater than 3, greater than or equal to 3 are two different probabilities, because greater than or equal to 3 includes 3. Greater than 3 does not. And this happens with discrete random variables. So notice the symbols make a difference. All right, let's look at an example with playing roulette. One wager players can make in roulette is called a corner bet. To make this bet, a player places his chips on the intersection of 4 numbered squares on the roulette table. If one of these numbers comes up on a wheel and the player bets $1, the player gets his $1 back plus $8 more. Otherwise, the casino keeps the original dollar bet. If X equals net gain from the single $1 corner bet, the possible outcomes are X equals -1, which means you lose the dollar, or X equals 8, you get a profit of $8. Here's the distribution of X. So the value, you could either get -1, which is lose $1, or you get a profit of 8. So it shows you the possibility. So there are 4 corners, so that's why it's 4 out of the 38 for the $8. That's a corner bet. And then the value is -$1 of -$1 is 34 out of 38. Okay, so if a player were to make this $1 bet over and over again, so many, many times, what would be the player's average gain? So the way we would find this, I'm going to break it down and show you the easiest way to find this. But this -1 is going to happen 34 times. The $8 will happen 4 times out of a total of 38. So this is average. You would add these up and then divide by the 38, which, okay, that makes sense. And then the next one, an easier way to write it would be 34 times -1, 4 times the $8 profit out of 38. But an easier way to write it is this last one right here. You would do your value times your probability plus your value times your probability. This is kind of like a weighted average, which that's how grades are formed in classes. The averages are weighted. Daily is worth a certain amount, and tests are worth a certain amount. So this is similar to a weighted average. So whenever you do this, it comes out to be -5 cents, basically. So that means an average loss of 5 cents. So does it make sense to play this over and over and over again? Average loss of 5 cents. Maybe that's why I don't play roulette. Okay, how do you calculate the mean, which is also called the expected value of a discrete random variable? And is it on the formula sheet? This is how we calculate it. Mean of x is the same thing as expected value of x, so E of x. It's found by doing the summation of xi times pi, which is what we just did with roulette. We did the x, which was losing $1, times the probability of losing $1. And then we had to do it again, so summation, so you add the next one, gain $8 times its probability. So you do this over and over and over again. So it is on the formula chart, so you don't have to memorize it. And then how do you interpret the mean expected value of a discrete random variable? So this is kind of our template. If a player makes a dollar bets many, many times, the average loss will be 5 cents per bet. Okay, so many, many times, it happens over and over and over again. The average loss, so see how it says average loss instead of saying the average gain will be -5 5 cents. That's kind of how you phrase it whenever it's a negative value. Okay, so the deal is many repetitions, many trials. And then it's an average, estimate, or approximate. So that's the value here. You wouldn't say the loss will be that per bet. You would say the average loss will be, because it's not guaranteed. Okay, expected values. Calculate and interpret the mean of the random variable x in the languages example on the previous page. Okay, so we are going to do the expected value. So this is where you do 1 times that, 2 times that, 3 times that, 4 times that, 5 times that, and you add them up. So 1.457. So in this case, it'd be 1.457 languages. So if we were to randomly select many U.S. high school students, the average number of languages spoken is approximately 1.457. So I understand that this doesn't quite make sense, because you're like, you can't speak 1.457 languages. But let's say we surveyed a bunch of students, then what we would see is if we average their languages spoken, we would get something close to this, is what it's saying. So does the expected value of a random variable have to equal one of the possible values? No, because this is an average. It's going to come out as a decimal, and that's okay. We don't want to round it. So no, the expected value is a mean, so it does not have to be a possible value in the distribution. So it's okay for it to be a decimal. This is what you would write. If we were to randomly select many U.S. high school students, the average number of languages spoken is approximately 1.457. Okay, and so what I want you to do is resist the urge to round expected value numbers, because it's a mean, and it's okay for the mean to be a decimal. All right, I will see you in class.